You all heard me because I was loud in the room, but the people online probably didn't, but I didn't say anything that they need to hear. So we'll start with our first speaker of the session, who is Sharan Agrawal, and he will be talking about the work that he's been doing, that he did in his MPhil, which looks at agent-based models for investigating the questions we're interested in, and I'll hand over to him.
Okay. Cool, thank you very much. All right, really excited to speak to you guys here. So I'll be talking about some work that I did during my MPhil with Anil and Keshav at Cambridge. In particular, this is about scalable agent-based models. Actually, there's two key things over here. There's the word scalable and the word optimized. And the key point of this presentation is to talk about how we can take models and turn them into something that is useful for policy design, both by sort of like scaling them to the kind of like scales you need for policies that affect the planet, so planetary scales, as well as trying to give decision makers the ability to pull levers in a systematic way, rather than just throw guesses at a model and hope it kind of works. This is particularly, we examined this particularly in the context of the applications to the economics of biodiversity and carbon. So I'll be speaking about it through that lens, but hopefully it's something that's transferable to other areas as well. I feel like most talks about climate change begin with like a doom and gloom statement. So this is no different. We all know that we're in the middle of sort of several existential crises, including climate change and sort of the decimation of global biodiversity. And while scientific advancement is pretty critical to meeting these challenges, it's really transformations in the aggregate behavior of society that will be instrumental in deciding how we meet these challenges and whether we do. And that really comes down to policy. Policymaking is incredibly hard. It is difficult to get global coordination, and once policy is made, it's incredibly difficult to change, and it has a lasting impact on all of our futures. So therefore, there is a need to make policymaking easier, or there's a need to build something, a tool that policymakers can use in which they can experiment more effectively with different hypotheses that they have before actually sort of going to the table and negotiating them with other parties. And while no model is correct, some are definitely useful, and a useful, understandable model that's expressed in the right framework and gives policymakers the tools they need to be able to make the decisions or do the experiments they need to do can be very valuable. Now, there is a bit of a gap. So traditionally, environmental policy uses integrated assessment models that rely on DSGEs, dynamic stochastic general equilibrium models, and that effectively means it's a type of model that makes a lot of assumptions, including rational agents and behavior that's occurring in a completely equilibrium context, which by definition, things like climate change are not. So there's been an increased use of ABMs over the last decade or so, and probably hopefully continuing something that will continue to happen, an increased use of ABMs as alternatives where you can capture very nonlinear emergent phenomena by basically simulating the behavior of different agents, each with their own state in a sort of like context and letting that play out and observing the output. It's basically just a different type of model that doesn't rely on those kind of assumptions of rationality and equilibrium. Now, there is a gap between what ABM frameworks right now we think can do and what is actually necessary for these kind of policy designs to happen. Critically, the ease of use, the ability to scale, and most critically, large-scale parameter calibration is something that ABMs don't do very well. If you think about an ABM that has, let's say, 1,000 agents, you have 1,000 parameters you need to calibrate. Most econometric models don't really get up to those scales. So that's something we try to address. And some of the key contributions of this work are developing this library called Salvo, which basically tackles like point 2 and point 3 that you'll see there, which is how do we actually take advantage of things like vectorization, hardware acceleration to achieve scale, and also distribution, and how do we also take techniques from machine learning literature and apply that to massive scale calibration of parameters in ABMs. The first part I won't talk about so much in this presentation, but I just wanted to use it to set context. We developed a model called the VDSKB, full form is over there, which builds on a model called the DSK, which integrates the economy and the climate, and we modified it to also include a feedback from the biosphere, using work done by Das Gupta, a very influential economist on the economics of biodiversity. That was the kind of context we were trying to implement in. So very much a real-world model that's highly complex and nuanced that we hope to sort of scale. So we identified kind of 5 criteria that like an ABM framework needs to achieve to actually be useful at policy design. Scale. Planetary scale ABMs will definitely need to be able to scale across networks of devices. They'll need to be able to take advantage of hardware acceleration to really achieve, the kind of speed we need for these kind of simulations. Most critically, they'll have to be usable. It would be great if we could get this into the hands of non-CS expert scientists who are able to use frameworks that don't require, figuring out how you can do message passing between different nodes in order to achieve distribution across different channels. Calibration is incredibly important. No model is useful without calibration. You need something that takes a model, fits it to observed data, and then determines whether it's useful or not. Finally, something that's very useful is also creating optimized policies endogenously within the framework itself. You have thousands of levers to pull in agent-based models. You can guesstimate what those, how to pull those levers, or hopefully we can have a framework that actually allows you to optimize those levers and figure out if you are asking a particular question or trying to optimize to a particular goal, what would the levers, what would be the best levers to pull and how. So, this slide is a lot, but intuitively, an agent-based model is quite simple. You take a bunch of different agents, give each of them their own state and their own set of actions, and you put them in environments where they can interact, you simulate them, and you study the results. And there's many different formalisms that can fit this pattern. For instance, Flame uses a communicating X machines-based formalism. Over here, we developed one from scratch by making a super basic observation basically, that says, the only real input to an ABM is the initial state and the configuration. Now, if you can formalize a bunch of different parts of the ABM into different chunks like this, we can just separate it out just to keep it clear in our minds. In particular, we can start with a set of, let's say, agents of a bunch of different types, J different types. You give each of them their state, and you can partition the state between a shared state where agents have to kind of collaborate together to update it, and a state which each agent owns themselves, and you can solve the problem of updating shared states using a dependency graph. You can also give them a set of exogenous inputs in the context of messages. You can also give them, critically, agent functions, which are like agent state is updated by a set of agent functions which express the actions of those agents on its state and broadcast those state updates to basically all the agents that they're connected through an edge graph. And that you can see that this takes inspirations from data flow computing models, where every node is effectively an agent that's kind of passing state to each other and updating the state based on all the received inputs. This is pretty abstract, so let's talk about something that's not really that much less abstract, but hopefully should make it a little bit more clear. One of the goals of ABMs is to compute measurements of the final state. Let's say you're creating a model that tries to predict what temperature is going to be 20 years from now, and you want to see whether it's 2 degrees, 3 degrees, 5 degrees, whatever. So that could be one stated outcome of an ABM, and one of the components in the formalism is a set of measurement functions which summarize the agent state, and that can be used as targets for both calibration and optimization. So if we wanted to compute the measurements of our final state, we can actually see using this formalism that this kind of breaks down very elegantly and recursively as repeated applications of an agent-based function. And what you get down to when you just expand this all the way down to the bottom is just your initial state and your set of parameters. And this is actually pretty powerful because if your agent functions in this kind of formalism are differentiable and deterministic, then the ABM itself is differentiable. And that's really cool because then you can calculate basically the gradients of your measurement function with respect to parameters and use backpropagation to train this at neural network scales. And even in the case where you don't have differentiable deterministic agent functions, we proposed a method where you can use reinforcement learning with Gaussian process surrogate models of the agents to kind of achieve something that's still pretty scalable, not quite to the same level. It's not something that I'll go to too much in this presentation. It's definitely more art than science, but that's definitely a very interesting avenue to explore. So, okay, I was wondering about this slide, but there's going to be a lot, and it's definitely a lot. So. I'll ignore this. And what I'm going to say is that we implemented Salvo basically based on a formalism as a wrapper around JAX. Why JAX? Well, basically to take advantage of the work of hundreds of engineers who worked on it and built it into something very powerful. But effectively, if our agent functions,
some of us don't know what JAX is.
Oh, sure, yeah. JAX is basically a HPC framework in Python, sort of like PyTorch and TensorFlow. It abstracts how code is executed away from the user. So the user defines, I want to do this computation. JAX says, okay, let me take that computation, let me compile it into something that is either specific to a particular device, like a GPU, or tries to optimize it for the platform that it's actually running on, and goes and executes it in a way that's way faster than just writing a for loop in Python. So another way to say it is just a common machine learning library that people use. And it can be incredibly, so we considered sort of like many different frameworks like PyTorch or like PyTorch or TensorFlow, but JAX ended up being sort of like a winner among sort of many different dimensions. Happy to discuss that, but I'll move on to the next one just because I want to keep this on time. So in order to actually make this concrete, like what this actually represents, what Salvo is, and how you actually use it, I won't talk about the VDSKB model in much detail, but the key thing to take away from this slide is it is a complex real-world ABM that tries to integrate basically economic flows, like a model of the economy, along with a model of, like a simplistic model of the climate, and take that and integrate that with a model of the biosphere that we sort of like took inspiration from the Script report for. And while the key thing I wanted to illustrate with this slide is that while this can be complex, while this models a bunch of different things, ultimately the equations that govern, or say that decide what's happening are pretty simple. They're just multiplications, divisions, additions, nothing really all that nuanced. And because one of the key ways in which we can take advantage of computation through JAX is if agent state can be made representable as tensors, you can get massive efficiencies through hardware acceleration. You can get them executed across things like TPUs and GPUs in a very effective way. So how does one actually implement this model in Salvo? Salvo is basically a transpiler that goes from a DSL to an actual JAX program that executes. It's relatively straightforward in the sense that all you really need to do is take 4 steps. You need to, in your ABM, you need to identify what your agent functions are and vectorize the implementations where possible. You need to define the state flow between different agent types. You need to define also the dependency between how different agent functions activate, like when does each one run, and that has a lot of opportunities for parallelism. And then finally, you define what the initial state is and the parameters, and you go and execute it. And like this is still pretty abstract, so let's look at some concrete examples of ABMs. This is one in which you have, it's called the forest fires ABM. You have a grid that has a bunch of trees, and you have fires that are set at random points in that grid. We simulate basically what happens to that forest based on a set of rules, and along with random regrowth, and see how that forest basically initially burns down to an extent and then regrows over time. So this is just a classic ABM that we use for illustration, and this is an example of the dependency graph that we can define as well as the state flow graph, where each of our agent functions, and agent functions is a pretty broad term here. They're expressed as what can basically execute now versus what needs to wait for other things to execute before they can start running. The Salvo transpiler takes that, converts it into a computation graph. You can see that roughly from this algorithm, and that computation graph is then sort of executed via JAX. Now, this is another example of what the actual code looks like for Salvo. You define your agent function. In this case, is for an ABM called circles, where you just have a bunch of circles which decide where to move based on all the other circles around them. So it's something that is theoretically quite difficult to compute. It's something called the fixed radius nearest neighbor search, but is also still pretty implementable in Salvo, where you have one agent function that computes what every agent should be doing. You have your initial set of parameters, you have a state flow and dependency graph, your initial set of initial state, and then you simply import Salvo, build the simulation, and execute it. So going quickly into evaluation, we built the VDSKB model, again, a fairly complex real-world model within Salvo, and 2 things kind of jumped out. Number one, because we used Python and JAX as sort of a basis for Salvo, because of one of our goals of usability, the number of lines of code that we needed to use to implement VDSK was actually not much at all. Like it was 2,000 compared to 9,000 for the DSK implementation, which used another ABM framework called LSD, which uses sort of like a C++ based DSL. Moreover, the time taken is actually pretty good because again, we're taking advantage of JAX built by, I think it was, so built by Google, which has incredibly optimized code that's actually running these computations underneath the hood. And even further to that, when we scaled the model to, let's say, 5 times bigger, Because our agent states were able to still fit in GPU VRAM, there wasn't really that much of an overhead in computing that. You just had more threads basically running on the GPU to do the computations and spitting back the same results. Whereas LSD, which is albeit compiled code running on a machine, actually did scale, as the agent state's size scaled. Similarly, we have pretty good execution performance compared to some other modern frameworks like agents.jl, which is a brilliant AVM framework in Julia. And also Flame, which is a C++-based framework which also supports GPU acceleration. Now, two quick things to talk about are the evaluation for basically what happens when we try to create optimized policies through Salvo. So what we're trying to do here is this is an ABM which consists of basically a bunch of different birds that are spread across a grid. Now, the raison d'etre of the birds is to converge to a centroid point. In a default world, they'll converge basically to the center. And what we're trying to do is get them to move their centroid from here to about here, so slightly to the lower left corner. Now, that's actually a pretty non-trivial thing to do because it requires the coordination of all these different birds, to move the centroid of the flock. And using backpropagation, we learned about 50,000 parameters, like neural network scale of parameters, that learned a very non-trivial policy per bird to figure out how to do this. And what actually happened is that a bunch of birds were flung out into the distance, sort of along this edge and that edge, in order to actually move the centroid of the flock while the other birds were converging to that lower left corner. And only when that centroid had moved did the other birds sort of converge back to a point. So that was actually a pretty good, useful application, or pretty interesting applications of backpropagation. And we also had an example of reinforcement-based learning for a stochastic non-differentiable ABM. But I'll quickly conclude with just some future avenues of research. Salvo is a transpiler, so it works best when you can figure out how you can place your agent state best across different devices, right? So figuring out how we can do device placement optimally, figuring out how we can actually accelerate, represent state as tensors most effectively, how we can help users build agent functions which are vectorized and able to take advantage of these speedups. These are all really interesting open research avenues that we can take to this just very initial experimentation. So I'll stop there if anyone has any questions or if you have time.
Do we have any questions? One at the front here.
So do all the agents share the same policy, or each of them has a unique policy?
That's a great point. The way that I implemented it was every agent of the same type is implemented as sort of like an individual agent function, but you can have agents of different types that have different agent functions. So you can have arbitrary different policies, but you might have like one agent, a human who is a banker, let's say, who has the same policy but different state and therefore behaves differently, and you can implement that as like one big vectorized function that's operating on their state.
Yeah, so each type of agents will have a different set of actions, available actions?
They could have a different set of actions, they could have a set of different state, different measurement inputs, different measurements, etc.
Yeah, so how do you evaluate the value or the score of their collective actions?
Yeah, so the collective actions produce an update to the state. And if your state is represented as basically tensors, you can run another function on that state to compute whatever your measurement is. So let's say that you had, for example, a bunch of different firms that were working, so that were operating in an economy, they produced emissions. Your agent function would take the current state of the economy, produce the new state of the economy plus emissions. And then you could have a measurement function which computes, for instance, does a summation across all those emissions to say, okay, in this period, all the firms that are running produced X amount of CO2. So it's just running more functions on state.
So do you use a critic network to evaluate the state, the value of the state?
Nothing so fancy. Like in this case, you just have a vectorized function, whatever vectorized function you want. It can be arbitrarily complex or super simple. In this case, you just sum it. Like you have your state represented as a tensor, you find the right part of the tensor to sum, and you sum.
All right, thank you.
Okay, question at the back there.
So just in terms of programming languages,
Yeah.
I understand this is a Python embedded DSL that you write things in terms of agents, which then compiles to a Python embedded DSL that writes things in terms of tensors, which then compiles that to GPUs and whatever fancy things. Okay, I just wanted to get that straight.
Yeah, relatively.
And what support is there if you could write some fancy agent thing that doesn't compile well to tensors? What happens then?
So the middle layer, like the JAX transpiler, is just taking your JAX code and converting it into slightly more like different JAX code. So that part, is very much just a piece of research software supported as research software R. But the main kind of issues that you'll see are probably at the JAX level, and for that you just have to engage with the community to try and figure out whether there's a solution or something, a new feature that needs to be added.
So the kind of the line between JAX and Salvo is permeable.
It's thin, yeah. It's an expression of the formalism in JAX in the form of a transpiler.
Okay.
Yeah.
Good.
Thank you. Any other questions? Okay, let's thank our speaker again.